So now we're going to talk about improper integrals. So what exactly is an improper integral? Well, before we talk about this, let's talk about what an integral was previously. So if I had some integral, some definite integral from a to b of f of x dx, right? Just a basic definite integral. I have a few requirements. Now, we never really talked about these requirements because they were always fulfilled with any integral we were given. And these requirements are that f of x must be bounded and finite for us to find this definite integral being the area under a curve. Now, when I say bounded, I mean I must have an upper bound f of x. If I'm doing this with respect to x, I've got a right bound b and a left bound a. Right? So we must be bounded on all sides finding this area. My lower bound is just going to be the x-axis if I just have some f of x. So when we talk about this finite, we mean we must have a finite area. So this cannot be an infinite area. And so what we're going to do today is we're going to break both of these rules. We've got two cases that we're going to deal with. Case 1 is a situation in which I've got 1 over x dx. Okay, pretty normal integrand. But now one of my bounds is infinity. So I'm going from x equals 1 to x equals infinity, which we can't really mark on our graph. And so I want to find this area under 1 over x from 1 to infinity. Now we can see that this doesn't have a right side bound. Since this curve is an asymptote, this 1 over x, we know that it's never quite going to touch the x-axis. So we're never going to have that right side bound. The second case, case 2, in this case, I've got bounds from 0 to 2. So my x bounds are finite now, from 0 to 2, but I have a discontinuity somewhere. So I want the area from 0 to 2, in this case from 0 to 1 underneath the x-axis, and from 1 to 2 above the x-axis. But the problem here is that now I have no upper and lower bound respectively, because again, in an asymptote, this curve never is going to touch x equals 1. And so these are our two cases. And you might be thinking, okay, well, if this is an asymptote, well then, if I have no right bound, I'm not going to have a finite area. And sometimes that's true, and sometimes it's not. And so this is our course of action. We're going to start off with a case 1 situation. And again, that's the situation in which one of our bounds is either negative infinity or positive infinity, or this applies too if both of our bounds are infinite. So if we have negative infinity to positive infinity. So if a boundary contains any form of infinity. So what we're doing is we're replacing this infinity with a variable. Let's call that variable t, because I can't really plug infinity into an expression. But when I plug infinity into an expression, when I want to know what a function is doing close to a positive infinity or a negative infinity, I'm thinking of a limit. I want to know what happens as some value approaches infinity or negative infinity. And so this is what we're doing. We're rewriting this integral as a limit. And so we're using whatever variable that we're replacing this infinity with. We want to find the limit as that variable, and we're just going to say t because that's the variable we're going to use. Now we want to find the limit as t approaches infinity. Because if I've got a variable in one or both of my bounds, that's okay. I can integrate that, just not with something as abstract as an infinity. And so let's do an example of this. In example 1, we want to determine whether the integral from 1 to infinity of 1 over x dx is convergent or divergent. And so when I say convergent, I mean the limit is finite. When I say divergent, I mean if the limit is infinite. And convergent means this has a definite area. If this is convergent, it means my area is a constant. And so far, when we're talking about the area under a curve, any area is going to be a constant. When this diverges, it means I have an area of some form of infinity. And so to find whether this is convergent or divergent, let's take this limit and replace this infinity with t. And so generally we want to sketch this out. And so I'm just going to sketch. Now I know I've got two separate curves that correspond to 1 over x, but I'm just going to sketch this right-hand curve because all I'm worried about is the region from x equals 1 to x equals infinity. And so my sketch doesn't have to be anything super crazy. I'm just worried about the first quadrant, and I can just kind of sketch this here. This is going to be y equals 1 over x, and I'm starting at x equals 1. And I want to find if this area is finite or infinite. Okay. And now my method tells me that I am turning this integral from 1 to infinity of 1 over x dx into a limit. So I want to replace this infinity with t. So I'm rewriting this as the integral from 1 to some t, and I'm finding the limit as t approaches infinity. You see what we're doing? So we're turning this from an improper integral into a definite integral with our variable t. And now I'm just solving this normally. I've got 1 over x dx. And I know the antiderivative of 1 over x is the natural log of the absolute value of x. Great. And because I have a definite integral, I know my bounds of 1 and t. All right, and I know I'm going to plug in this t and subtract from it the natural log of 1. So I'm going to get the natural log of the absolute value of t minus the natural log of the absolute value of 1. All right, so let's simplify this as much as possible first. That's always easiest. Now, what's the natural log of the absolute value of 1? Well, I know that's just 0. And so this term is just going to be 0. And so I am left with, now let's remember that we're taking a limit. I'm left with the limit as t approaches infinity of the natural log of the absolute value of t. Now with a limit, I remember all of my rules of limits, and the first thing I'm going to try to do is I'm going to plug this in to my function. And I've got the natural log of infinity. Now I can't actually evaluate the natural log of infinity. It's kind of an abstract idea, but what I'm wondering is what happens as the natural log of t, what happens as this t gets larger and larger? And if I don't know what this is, I'm going to revert to my calculator and graph this function. So this is my course of action. I'm going to go into y equals, and I'm going to graph the natural log of the absolute value of t. And you can find absolute value in math over to number and number 1. So that's absolute value in our calculators. And if you have a newer version, it'll show up as these absolute value bars. And now I'm going to just type in my variable. And while I have x in here, I just want to know what happens as this variable gets larger and larger. My calculator is going to call that x. And so let's go to maybe like a standard window. Let's zoom 6 this. And I want to know what happens as x gets larger and larger. Maybe I can adjust my window so that my x max is 100. Now let's see what happens. Well, while I'm going up slowly, can I see that as x gets larger and larger, my y value is still going to continue to increase? What that means is that as t approaches infinity, the natural log of the absolute value of t approaches infinity. And so this is going to give us a limit of infinity. And because our limit is not finite, limit is infinite, this is going to diverge. And if you see these little 3 dots, this is just a mathematical symbol for therefore. So the limit is infinite, therefore this is divergent, or you could say this diverges. And this kind of makes sense, right? If we don't have any right bound and this is going and going and going, now the height between the x-axis and this function is getting smaller and smaller as we move to the right. We have an indefinite area. Our area is still infinity. As we go further and further to the right, this area is just increasing by a smaller and smaller margin, but it's still continuing to increase. And so let's do another example. In example 2, we've got a similar situation, but now we want to determine whether the integral from 1 to infinity of 1 over x squared dx is convergent or divergent. And so before I do anything, I want to graph this. It's never a bad idea to graph these functions first. Always kind of a good course of action. And so 1 over x squared. And let's go to a standard window first and see what this guy looks like. And I'm only worried about the area from 1 to infinity. Now our calculator might not give us a great idea of what this looks like, but let's rearrange our window a little bit so I can see that this might be an asymptote. That's kind of what I want. So I want to decrease the y values and I want to increase the x values in my window. So I want my x to go from, let's start at 0 because we're not worried about anything less than 1. Let's go from 0 to 100. Let's go up by 10. And let's change my y scale from 0 because I know this is going to be positive. And let's change my y max to, I don't know, maybe 2. Does this give us a better idea? Well, we're still getting like a sharp downturn. And let's change my y value from 0 to 0.1. And while this cuts off, we can get a better and better idea that this is asymptotic. Let's change this y value max to 0.01. Okay, an even better idea of what this looks like. So we can see that this doesn't have a right bound. We can see that this forms an asymptote. So let's do a quick sketch of this. And it's going to look exactly like the problem before, but we saw a sharper trend toward the x-axis. So I'm going to get closer to the x-axis more quickly. Okay, that's as good as we're getting. Y equals 1 over x squared. And again, we're just worried about the area from x equals 1 to infinity. I'm worried about this area under here. I want to know if it's finite or infinite. And so let's move toward our method here. So we've got the integral from 1 to infinity of 1 over x squared dx. And like in the last problem, the issue here is that I've got an infinity at one of my bounds. And instead of writing this with an infinity at one of my bounds, I'm going to replace this with the variable t. And I want to know the limit as t approaches infinity. And I've got the same thing going on in my integral, so I've got the same integrand. And now I'm just ready to integrate normally. And I'm remembering that 1 over x squared is something that I can write as x to the power of -2. The reason I write this is so that I can more directly use that power rule, because now I know that I'm adding 1 to this power. So this is going to become an x to the power of -1, and I'm dividing by that new power. And all that's going to do is that's going to flip the sign. And now instead of an x squared in the denominator, I just have an x. And so this is going to turn into a -1 over x. And my bounds go from 1 to t. And so before I'm worried about this limit, let's plug in our upper and lower bounds. We know we're taking -1 over t and subtracting this from a -1 over 1. And we said we'd like to simplify before worrying about a limit. Well, when I'm subtracting a negative 1 over 1, I'm just going to call this a negative 1 over t plus 1. And now I want to find the limit as t approaches infinity. And I'm dealing with each of these terms. So when I plug in infinity to negative 1 over t, this is going to approach negative 1 over infinity plus 1. This plus 1 isn't going to change. And so negative 1 over infinity, well, as my denominator of a fraction gets larger and larger, this fraction is going to get smaller and smaller and get closer and closer to 0. And so I just sometimes like to draw this arrow with a 0 to say that this goes to 0. There's different notation you can use. You don't have to use this one. And so this goes to 0 plus 1 as t gets larger and larger. And so my limit is just 1. And because my limit is a constant, so this limit is a constant, therefore this is a finite area, therefore this is convergent. The way I like to write this is I like to say it converges to 1. When this converges, when we have a finite area and it's some definite area, we like to put what that area is. And so we'll write converges to an area of 1. And so what this means is that although I don't have a right bound, although this blue curve y equals 1 over x squared is an asymptote, it is never touching the x-axis. It's steep enough so that I have a finite area. And there are a couple examples from our real world that kind of help us make sense of this. And so you might have heard of the example of someone walking halfway across a football field. So if I walk halfway across a football field, and then I walk halfway across the remaining distance, and then another halfway across the remaining distance, well, technically, I will never stop moving. I'll never walk further than the entire length of that football field. If you play this game called Apex Legends, there's this character named Octane, and they have this ability where they can lose 10% of their health to speed up for a few seconds. And so the idea here is that they can use that ability over and over again and keep taking off 10% of their health, and then 10% of the remaining health that they have left. Continue to do that, but that will never actually end the game because they'll always have a small portion of health left. So we can see a lot of these ideas around us in our real world, as abstract as this may seem. So now let's summarize what we just found. If we have the integral of 1 over x from 1 to infinity, we found that this would be divergent. We've got an infinite limit, meaning we've got an infinite area. If we've got the integral from 1 to infinity of 1 over x squared, we found that this has a finite area. This area is 1. So can we make a conclusion? And so this is for the unique situation when we have an integral from 1 to infinity, and we've got this in the form of 1 over x to the power of p. And so looking back at these two examples, we found that if p is equal to 1, we have an infinite area. If p is equal to 2, we have a finite area. And so if p is greater than 1, this is convergent, like we found with this 1 over x squared. And if p is less than or equal to 1, this is divergent. We've got an infinite area. And so we can always use this theory if we've got the area of 1 over x to the power of something, but only if our bounds are from 1 to infinity. So this is important only for these bounds. So now on to another example. We want to determine whether the integral from 1 to infinity of e to the power of negative square root of x over the square root of x is convergent or divergent. And so as always, let's start with graphing this. So I want to graph e to the power of negative square root of x divided by the square root of x. And let's start with a standard window. And I kind of see what this thing looks like. If I can narrow this down to the first quadrant, because I see that's where everything's happening, I could get somewhat of a better idea that this is just that asymptote going on to positive infinity. And so I can sketch this, and the sketch of this is not really going to look different than the sketch of my other functions that I found, because it's still just going to look like this asymptote. And this is going to be y equals e to the power of negative root x over root x. Again, going from x equals 1 to infinity. And I can't use that rule I just found because now this is no longer in the form of 1 over x to some power. But I'm going to use my usual technique of finding the limit as t approaches infinity. So I'm replacing this infinity with a t. So I'm taking this from 1 to t with the same integrand, e to the negative root x over the square root of x dx. And I'm taking this limit as t approaches positive infinity. And so now to integrate this. So I've got a couple problems here. Number one, I've got a quotient. I don't really have an integral rule for quotient, so I need to do something about it. The other problem is that I've got a negative square root of x in my exponent. Because I know when I have e to some power, that power has to be just a variable, I'm going to allow my u to be equal to negative square root of x. We said that we're essentially allowing u to be equal to whatever the problem in here is. What's the biggest problem? And so then my du is just going to be the derivative of negative square root of x. And this is going to be negative 1 over 2 times the square root of x. And the way I like to think of this is I like to think of this as my u is negative x to the power of 1/2. And when I take that derivative, I'm going to use the power rule, and I'm multiplying this 1/2 by a negative 1. So this becomes negative 1/2 times x, and I'm subtracting 1 from that power. So this becomes an x to the power of negative 1/2. All right, and so I've got my u and my du, and I cannot forget to put that dx on my du. Now I can almost get ready to replace this integrand with everything in terms of u, but I don't see a 2 in here, and so I want to rewrite this as 1 over x dx, because I've just got 1 over the square root of x. This is my dx, right? A square root of x in the denominator is like 1 over the square root of x. And so if I multiply both sides of this by negative 2, in other words, if I divide by 1/2, by negative 1/2, I'd be left with negative 2 du is 1 over root x dx. And so I'm going to put this coefficient of negative 2 in front of the integral. And I'm left with the integral of e to the power of u. And now I've got my du. I know the antiderivative of e to the power of u, it's still e to the power of u. And I know when I turn this back into terms of x, I'm going to replace that u with a negative square root of x, and I'm left with negative 2e to the power of negative square root of x. Now that I've got everything back into terms of x, I can add my bounds again, because these bounds, remember, are in terms of x. So I've got my bounds from 1 to t. I am taking the limit as t approaches infinity, but let's simplify this first. What that means is wherever I see x, I'm plugging in a t, and so I've got negative 2e to the power of negative root t. I'm subtracting a negative 2e to the power of negative square root of 1. Let's simplify this a little bit. Now this first term, I can't do much with it. However, if I've got a negative square root of t in the numerator, I can make this a positive by putting it in the denominator. I can put this as a negative 2e to the power of positive square root of t. This is kind of a personal preference of mine, that when I see a negative in the exponent and I want to evaluate a limit, it's a little bit easier for me to make this a positive exponent. I can do that by switching levels, switching this from the numerator to the denominator and vice versa. I know when I subtract a negative, I'm adding, and when I have an e to the power of negative square root of 1, well, the square root of 1 is just 1, so an e to the power of negative 1 is the same as an e to the power of positive 1, or just an e in the denominator. And so this is a constant, and so now I'm just looking for the limit as t approaches infinity of this expression. And let's see what happens. Well, looking at this first term, negative 2 over e to the power of the square root of infinity. So as e to the power of some value gets larger, let's remember what our e to the power of the square root of x looks like. So if I delete this negative and delete everything over to the right, let's see what this looks like. Can I see that as x gets larger, my y value also gets larger? Bringing us back to a standard window, I see the same thing here. And so as my exponent gets larger and larger, closer to positive infinity, this denominator gets closer and closer to infinity, and this just turns into 0. And so this is going to give me 0 plus 2 over e, which is just 2 over e. And because this is a constant, this is a finite value, and therefore this converges to 2 over e. And that is it. Example 5, we want to determine whether the integral from 0 to infinity of 1 over 1 plus x squared dx is convergent or divergent. So let's bring that to our graph. Important note here, when I put this 1 plus x squared in the denominator, I need to make sure I have this in parentheses, because if not, my calculator is going to think I'm dividing 1 by 1 and then adding x squared. So just make a note of this. And let's go to a standard window and see what happens. And we can kind of see the deal here. I'm looking from x equals 0 to x equals infinity. And so let me just adjust my window a little bit. Let's start our y min at negative 1 and go to about 2. I saw it was kind of centered at this area around here. And so now I can see how this looks like an asymptote. Now I'm looking from 0 to positive infinity. And so let's do a quick sketch of this. And I kind of have this hump up at the top now with that same asymptote. And I've got y equals 1 over 1 plus x squared, with my x going from 0 to infinity. So I want to see if this area is infinite or finite. And in the same way as before, I'm taking this integral, I'm replacing this infinity with the constant t, and I want to find the limit as t approaches infinity, with my integrand of 1 over 1 plus x squared dx. And I'm thinking back to all of my different integration techniques. Now I could use trig substitution and put this tangent in the denominator, or I could notice that this looks a lot like one of my inverse trig derivatives. I'm remembering that the derivative, let's do this in terms of x, the derivative of the inverse tangent of x is equal to 1 over x squared plus 1. And so this leads me to the idea that the antiderivative of 1 over 1 plus x squared is going to just be the inverse tangent. Easy enough. So this is going to be the inverse tangent of x as x goes from 0 to t. Now let's plug in our t and our 0 and simplify this before trying to take that limit. And so I've got the inverse tangent of t minus the inverse tangent of 0. And I want to know what happens as t goes to infinity. Now, inverse functions can be a little bit confusing. Here's what I'm thinking. So I know that if I've got the tangent of theta being equal to some value, let's use, I don't know, pi as an example. If I want to solve for theta, I know that the theta is equal to the inverse tangent of pi. So inverse tangent, essentially what this does is if I have the inverse tangent of infinity, I'm thinking, what value of t is going to give me a tangent of infinity? And as far as tangent goes, if we know what the tangent of infinity is, great, we can answer this. But the way I like to think of it is that I know tangent of theta is equal to the sine of theta over the cosine of theta. Because I know what sine and cosine theta are because I can picture that unit circle. And so when I think of the tangent of infinity, if I think of tangent as sine over cosine, what do I want for infinity to happen? Well, I know as my numerator gets closer and closer to 0, my whole fraction is going to go to 0. But as my denominator gets closer and closer to 0, this fraction is going to get larger and larger, and this is going to go to infinity. That's why I'm thinking, what value of cosine is going to give me 0? Because my graph's in the first quadrant, I'm going to focus on these values in the first quadrant. And I know that a cosine of pi over 2 is going to give me 0. And so tangent, inverse tangent of infinity is pi over 2. Inverse tangent of 0, well, in the same way, I'm thinking, okay, the sine of what is going to give me 0? Because if I have a 0 in the numerator, we said that this whole fraction goes to 0. And I know that a sine of 0 is going to give me 0. And so the inverse tangent of 0 is 0. And so my limit is going to be pi over 2 minus 0, which is equal to pi over 2. And so this is going to end up converging. This converges to pi over 2, since we have that finite area of pi over 2. So now on to case 2, where we have a discontinuous integrand. So in this case, we're supposing that f of x is a continuous function from the left, meaning it has a discontinuity at b. So it has a vertical asymptote at x equals b. And in the same way as with our case 1 situation where we replaced infinity with t, we're going to replace the x value for which there's a discontinuity with t. So since there's a discontinuity at x equals b, we're replacing that b with t. So kind of the same idea here. The only difference is that in this situation we have a vertical asymptote. Unlike in our case 1 situation when one of our bounds was infinity and we had a horizontal asymptote. And so that's really the only difference, but our process for the most part isn't changing. So that's the good news. So the other important thing here is that now we're going to only worry about these directional limits, remember. So in this case, we've got a limit from a to b, and because b is the right bound, we're finding this limit as t approaches b from the left. This little exponent of a negative means from the left. If we were to have a b with an exponent that looked like a plus, this would be from the right. And the other thing that might make this case a little bit trickier is that if both of our bounds are constants, we might not always know where that discontinuity lies. And so this is going to be one of our steps, is to actually solve for this discontinuity. And remember, when we have a discontinuity, this discontinuity occurs when we have a negative inside of a square root, or if we have a 0 in the denominator, or if we have a negative in a logarithm, or a natural logarithm. So now we've got just a few situations that would lead to a discontinuity. And to be more exact, not just a square root, but an even root. So like a 4th root or a 6th root or an 8th root or anything like that. Okay, and like we said, our method is going to mostly stay the same. And so let's do example 7. We want to determine whether the integral from 2 to 5 of 1 over the square root of x minus 2 dx is convergent or divergent. And so we want to look for the discontinuity. So where is the discontinuity? Well, I see a square root. And so I know this square root can't be negative. So x minus 2 cannot be negative. But remember, I'm looking for a discontinuity on the interval from 2 to 5 inclusive, meaning I'm including both 2 and 5. And so what else can happen in the denominator? Well, I can't have a denominator of 0. And so if x equals 2, that would give me a denominator of 0. And so x cannot equal 2. So my discontinuity occurs at x equals 2. And so this is what I need to replace with a t. And just to make sure there are no other discontinuities on this interval, I'm going to graph this quickly. And when I graph this, I'm only worried about my window from x equals 2 to x equals 5. Let's go up by 1. And I know this can't be negative because of that square root in the denominator. And so my y min is going to be 0. So let's see what happens. Great. And I don't see any other discontinuities. Now that doesn't mean that there might be one of these removable discontinuities, so a hole in the graph that we can't see. And that's why we need to check both algebraically and with our graph to check for any discontinuities. And so just a quick sketch of this. From 2 to 5, and I'm just going to worry about from what this looks like from 2 to 5. And I can see back looking at my graph that it looks like I have a horizontal asymptote at x equals 2, remembering that we started off at x equals 2. So I have a horizontal asymptote at x equals 2. And I'll just draw this dotted line to show that. And I want to find out if this is a finite or an infinite area. Just labeling my function really quickly. Okay. And so now I'm replacing this 2 with a t because this is where the discontinuity lies at x equals 2. And so replacing my 2 with a t, I'm going from t to 5. And I want to find the limit as t approaches 2. But now this is important. I'm not worried about anything that goes on from the left of 2, right? It doesn't even matter what happens here. I'm only worried about this region from 2 to 5. So when I'm worried about the limit as t approaches 2, I'm only looking as it approaches 2 from the right. And so that's why I'm going to add this little plus to talk about the limit as t approaches 2 from the right. Now my integrand is going to stay the same, 1 over the square root of x minus 2 dx. And now let's integrate this. And I'm looking for the issue here. So I've got a square root of x minus 2 in my denominator. Here's what I'm thinking. If I make my u the square root of x minus 2, my du is going to be pretty messy. But if I just allow my u to be equal to x minus 2, then my du is just dx. And so I can rewrite this as 1 over the square root of u, which is the same as u to the power of negative 1/2 du. And now using the power rule, I can write this as u to the power of positive 1/2 divided by 1/2. So this is going to be 2u to the power of positive 1/2. And so I'll substitute that x minus 2 back in, and I get 2 times the quantity x minus 2 to the power of 1/2. And let me just actually write that as a square root. So 2 times the square root of x minus 2. Either way, really. And I am taking this from t to 5. And so let's simplify before worrying about our limit. When I plug in 5, I get 5 minus 2, so that's 3, and so I get 2 root 3. And I'm subtracting from this 2 times the square root of t minus 2. And now I'm looking at that limit. Got the limit as t approaches 2 from the right. All right. Now nothing happens to this first term when I plug in a 2, but when I plug a 2 into this square root, again from the right, so my 2 minus 2 is still positive because this t value is going to be slightly larger than 2, right? But this is getting closer and closer to negative 2 times the square root of 0 as my t gets closer and closer to 2. And so this is going to go to 2 root 3 minus 0. And because this is just a constant 2 root 3, I can say that this converges to 2 root 3. And so my area under this curve is going to be 2 root 3. So as you can see, this method is not a lot different than it was in case 1. The only added step is really finding this discontinuity so we can replace that with t rather than just my very obvious positive or negative infinity. And so let's just do one more of these. In example 9, we want to determine whether the integral from 0 to 3 of dx over x squared minus 6x plus 5 dx is convergent or divergent. And so to integrate this and to find the discontinuity, I'm first going to need to use some partial fraction decomposition. So I can find where this discontinuity occurs, so I can factor this denominator. So if I factor this x squared minus 6x plus 5, if I factor this quadratic, I'm going to have two factors. X is going to be the first term, and these second terms need to multiply to give me a positive 5 and add to give me a negative 6. So I've got a negative 5 and negative 1. That's going to give me zeros at x minus 5 equals 0 and at x minus 1 equals 0, meaning I'll have zeros at 5 and 1. Now I'm only worried about the interval from 0 to 3, and so I'm going to have a discontinuity at x equals 1. And so let's see what this graph is going to look like. And to plot this, I'm only going to be worried about the window from x equals 0 to x equals 3. And because now I can have negative y values, because if I have x values from 0 to 3, I can still get a negative y value. And so let's expand my window to a y min of negative 10. And now we get a good idea of what this looks like. We said that there would be a discontinuity at x equals 1, and there is. And so let's do a quick sketch of this situation. And we're capping this off at x equals 3. All right, and we are looking for this area. Now, because I'm dealing with two separate areas, this brings us back to kind of the same idea as in 6.1. Now my upper bound and my lower bounds are flipped. And so in this case, I need to use the idea that I'm separating these at that discontinuity. And so I'm going to break this up from 0 to 1 of this integrand dx over x squared minus 6x plus 5 plus the integral from 1 to 3 of this same integrand. Okay. Now, because this is discontinuous at 1, I'm going to switch over to my interpretation of limits, and I'm finding the limit on the left-hand side. I'm replacing this 1 with a t, right? And I'm worried about what happens for this left-hand integral as we approach 1 from the left. In this first area, I'm worried about us approaching 1 from the left. So using this notation. And I'm going to write this as 1 over, and I'll just write the factored form because eventually I want to be able to integrate this. So this is going to be the quantity x minus 5 times x minus 1 in the denominator. And this dx can either go to the numerator or it can go out to the right. And I know we're just kind of used to seeing it out to the right over here. Same idea as we go from 1 to 3. Now in this region under the curve, I'm worried about what happens as t approaches 1 from the right. And so this is going to be my limit as t approaches 1 from the right, from t to 3. Again, replacing that 1 with a t. And I'm again going to write this integrand as a 1 over x minus 5, x minus 1 dx. Now, if I've got the same integral with different bounds, I'm not going to do everything twice. I'm just going to pull out this integral and I'm going to just find this indefinite integral. And now how do I integrate this? Well, I can't really use u substitution. I could, but it'd be that kind of funky u substitution we talked about. But I see that I can break this up using partial fraction decomposition. I'm going to use partial fraction decomposition like we did in section 7.4. And so I know that 1 over x minus 5 times x minus 1 can be broken up into some a over x minus 5 plus b over x minus 1 because we have non-repeating linear factors. And so now using that idea of cross multiplication, I am multiplying the a by whatever is going to be multiplied by x minus 5 to get this original denominator, and so that's going to be x minus 1. I'm adding to that b multiplied by x minus 5. And this is equal to 1. And so if I distribute this a, I get ax minus a. Likewise with the b, I get plus bx minus 5b. And then I'm going to break this up into x terms and constants. And so I have that 1 is equal to x times the quantity a plus b. And then I'll add this to the constants of negative a minus 5b. And I know that I don't have any x's, so I can really see this as 0x plus 1 on the left. And so a plus b is going to be equal to 0. And negative a minus 5b is going to be equal to 1. Our constants must add up to be equal to 1. And so I can do just a little bit of algebra here. If I bring this b to the other side, I get a equals negative b. And then I can plug this negative b in for my negative a. So negative a is going to be negative b, which we'll really just call a positive b, minus 5b is equal to 1. And this will give me a b minus 5b, so negative 4b is equal to 1, with a b of negative 1/4. Using this first equation, this will give me an a of a positive 1/4, and I've got my a and b. And so this tells me that I can rewrite this integral as the integral of 1/4 over x minus 5 plus negative 1/4 over x minus 1 dx. Because I've got both of these terms that are added together, I'm going to separate these into different integrals, and I'm going to pull this coefficient of a 1/4 and negative 1/4 out to the front. And so I've got 1/4 times the integral of 1 over x minus 5 dx minus 1/4 times the integral of x minus 1 dx. Now, and I've got my 1 over that I forgot on the right. Okay. Now, what does this look like? Well, these both look like 1 over something. And I'm going to call that something u. And so on the left here, if my u is x minus 5, then my du is just 1 dx. And so I can call this 1/4 times the integral of 1 over u du. And I know this will give me the natural log of u. So I've got 1/4 times the natural log of the absolute value of u. Bringing that back into terms of x, I've got 1/4 times the natural log of the absolute value of x minus 5. In the same way, on the right-hand side, my u is going to be equal to x minus 1, which will give me a du of 1 dx. Or I could just write that as dx. Substituting in my x minus 1 for a u, I get that this is negative 1/4 times the integral of 1 over u du, which gives us negative 1/4 times the natural log of the absolute value of u, which finally gives us negative 1/4 times the natural log of the absolute value of x minus 1. Because both of these terms are added together, this will all give me 1/4 natural log of the absolute value of x minus 5 minus 1/4 natural log of x minus 1. Okay, and we are ready for that limit. So remembering that we're taking the limit, let me just copy and paste this down here. Let's remember what our goal is. So remembering that all we did was we evaluated both of these integrals. Now this is where I differ. I've got different bounds. And so I'm going to take the limit as t approaches 1 from the left of, and I've got 1/4 times the natural log of the absolute value of x minus 5 minus 1/4 times the natural log of the absolute value of x minus 1. And I'm taking this from 0 to t. On the right-hand side, I've got this same expression here, so 1/4 ln absolute value of x minus 5 minus 1/4 natural log of the absolute value of x minus 1, and now my bounds go from t to 3. And so let's plug in our two different sets of bounds. I'm going to start on the left here. And so I've got 1/4 times the natural log of the absolute value of t minus 5 minus 1/4 times the natural log of the absolute value of t minus 1. And then I'm subtracting from this both of these expressions evaluated at x equals 0. And so I'm subtracting from this 1/4 times the natural log. Well, 0 minus 5 is negative 5. And since I've got the absolute value of negative 5, I'm going to call this 1/4 ln 5. And then because I'm subtracting a negative, I'm adding 1/4 times the natural log of 0 minus 1, which is negative 1. Absolute value of negative 1 is 1. But I remember that the natural log of 1 is just 0. And so at this point, I am going for my limit. And so I'm finding the limit as t approaches 1 from the left of this expression. I'm just not worrying about that term that's going to give me 0. Okay. As I approach 1 from the left, of the natural log of t minus 5, well, t minus 5 approaches negative 4. And so I'm left with that absolute value, and so I've got 1/4 times the natural log of 4. Next term, I've got negative 1/4 times the natural log of 0. Now what happens as my natural log approaches 0? Well, let's bring out our calculators. If I'm just looking at the natural log of x, as x approaches 0, I'm going to get closer and closer to negative infinity. If I get a standard window, I can see that, and it still kind of cuts off here, but this is an asymptote at x equals 0 going to negative infinity. And so this is going to approach my negative infinity. We found that the positive natural log of 0 approached negative infinity. And then I just have this constant negative 1/4 ln 5. All right, so what really happens here? Well, I've got two constants. I'm subtracting one constant from the other, but that doesn't really matter. I'm left with a positive infinity. And remembering that this was the area of that first region, so let's go back up to our graph. This is the area above the x-axis. One more thing to mention. Now, we know that an area above the x-axis is going to be a positive area. An area below the x-axis is going to be a negative area. And so finally, even if my positive and negative areas cancel out, so let's say we got an area of negative infinity down here, it doesn't matter. This still diverges, meaning that we don't have a definite area. Even if our areas end up canceling out in some way, we still have a divergent integral. And so with that, there's no need to evaluate this second integral because we've already found that this is divergent. Because we've got one of our areas to be positive infinity, we can say that this is divergent. And one more important note here is that remember when we were talking about L'Hopital's rule, we talked about these different indeterminate forms. Now be careful when I have an indeterminate form with an infinity. So if I have a 0 times infinity, this isn't necessarily divergent because it contains an infinity. In fact, we then need to use L'Hopital's rule to get rid of this indeterminate form. If we have an infinity minus infinity, again, not necessarily divergent. Again, we have to simplify using L'Hopital's rule. But because we know one of the areas is infinity, this by definition diverges. And that is it for this section. It's kind of a strange concept, but it's got some pretty cool applications.